Good evening, good morning, and good afternoon to all my friends who are attending this webinar from different parts of this globe. Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur is organizing the webinar series, which is named as the Saturday Manufacturing Talks. We have started this journey from 13th of March, that is the last Saturday. Today is the second day of this webinar series. The purpose of this webinar series is to create awareness on different aspects of manufacturing, the research across in the minds of the people, residing different parts of this globe. At the same time, to have more and more interaction with the Center of Excellence at IIT Kharagpur. And so today is the second day. I would like to give you a little introduction about the Center of Excellence. And I'll also introduce today's speaker. The Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur. It has been established early 2018. So it's just 3 years old. And this particular, this Center of Excellence is dedicated purely for solving industrial problems. It is an industry academia collaborative platform. This has been set up with the strong support from the Department of Heavy Industries, which is under the Ministry of Heavy Industries and Public Enterprises, Government of India, and also forming a consortium of top-notch industries in our country. We do have 4 private industries. They are the Tata Group members, and 2 public sector industries. With these 6 industries, we started our journey, and the last year one startup has joined our consortium as well. The vision of the Center of Excellence is to inculcate the modern concepts into the manufacturing field so that the innovation can be brought out by adding value into it. We'd like to create an ecosystem between the large industries, small industries, and also the academic institutes. We'd like to collaborate with the international expertise while executing the different projects for the industries. We'd also like to give training to the people in the industries, particularly the MSME in the sector, so that, and also to help the startup. So while executing these projects, if any novelty comes up, the intellectual property that will also be secure. So this is the overall vision of this Center of Excellence. We are working on 4, the thematic areas. One is that materials, automation, additive manufacturing, and Industry 4.0. Presently, the OEMs, they have given us their problem, the statement, our faculty colleagues, along with the experts of the industries. We are working together to give solutions to them. We are also, giving training on different aspects of manufacturing to the MSME people, so that they get to know that what is happening in the industries, what is the need, so that they can get equipped and be ready to be added in the supply chain of the big industries. The Center of Excellence would like to work in the technology readiness level 4, 5, 6. So we'd like to catapult these academic innovations into the industrial practice. The advantage of the Center of Excellence is that we do have large scale, the industrial setup. So the upscaling of the academic concepts into industrial practice is very much possible at the Center of Excellence. We have created an innovation lab, which is having a large number of sophisticated, the state-of-the-art equipment, which are getting used to execute the projects of the industries who are working with us. These facilities would also be leveraged to the MSME and startup. I would like to show some of the unique infrastructural capacity of our Center of Excellence. This is a industry 4.0 enabled friction stir welding machine. Friction stir welding is a solid state welding method. It is getting used these days to join different dissimilar materials. We do have this, the robotic 3D laser scanning vibration testing facility. It can be used to measure the vibration, of an object at its different, the portion through scanning. We do have the acoustic holography as well to get to know the source of noise of any object. We are having this additive manufacturing, the facility, hybrid additive manufacturing facility. This should be, the use to print the object close to 1 meter length. It's a metal 3D printing facility. We are going to have this industry 4.0 compliant robotic welding facility, that is robotic MIG, robotic TIG, robotic spot, laser and the cladding facility, laser welding and laser cladding facility. These are all, the sensor integrated, so you can get to know about the process quality. You can also get to know about the health of the machine when it's performing. I'd like to briefly tell you about the recent innovations of the Center of Excellence at IIT Kharagpur. We have filed a patent jointly with the Tata Consultancy Services about developing a system which should be able to real-time monitor and control the quality of the product. We have taken up as a case of this friction stir welding, where through the sensors data we can predict. We have predicted the weld quality, and when the machine gets to know the quality of the product it is producing, so real time it is changing its parameter, and ultimately it is coming up with a defect-free way. This has given us a lot of visibility as well. Again, we have come up with a low-cost, real-time machine vision-based quality inspection systems. The developed systems would be very much useful for the MSME to check the quality in a mass production. So by using, why I'm saying the low cost is that here image is captured by just simple webcam. So whatever the image is coming up, we are applying AI methodologies to augment the image, the quality, and through image processing, we are finally detecting what is the quality of the product is producing. This has also been filed as a the patent. Then the center has come up with an algorithm to boost the profit in the manufacturing sector. So this is a case study which our faculty colleagues have done for the annealing furnace performance. So different components of the furnace is getting predicted this monitor, and how long it will be able to perform, that is also getting predicted in a real time. This has been used. This is our center of excellence. Thank you. Now I'd like to introduce our today's speaker. Dr. Nikhil Chopra is a professor in the Department of Mechanical Engineering at the University of Maryland, College Park, USA. Before joining the University of Maryland, he was a postdoctoral research associate in the Coordinated Science Laboratory at the University of Illinois, Urbana-Champaign from 2006 to 2007. He received a Bachelor of Technology Honors degree in Mechanical Engineering from IIT Kharagpur in 2001, an MS degree in General Engineering in 2003, PhD degree in Systems and Entrepreneurial Engineering in 2006 from University of Illinois at Urbana-Champaign. His current research interests include control of network robotic systems, bilateral teleoperation, and control of mixed human-robot teams. He is the co-author of the book Passivity-Based Control and Estimation in Network Robotics. He is currently an associate editor of Automatica and was previously an associate editor of IEEE Transactions on Control of Network Systems and IEEE Transactions on Automatic Control. With this, I request Professor Chopra to start his presentation.
Thank you, Professor Pal. If I can just get the presenter access, then I can share the screen.
Yeah, sure.
Okay, I got it. Good. So yeah, first of all, it's great to be at this, giving in the seminar series, and I'd like to thank Professor Pal and COE for kind of inviting me to give this talk. So today, basically, I'm going to be talking, partly about a lot of, basically brief overview of what I've been doing, what are my current research projects, and then focus a little more on soft robotics as we go on. Yeah. So, going back to 19 this is a recent picture though, but going back to 1980s or late 70s, a lot of the focus was in in manufacturing environments was a lot of the welding tasks and a lot of other tasks in automotive plants were basically being done by robots at that time. And so going from that stage, there was, if you remember, a lot of science fiction movies that were going on, and people were kind of imagining different things. I was growing up, movies like Terminator came about, so they are good to kind of kick up your imagination and what actually can be done. So now we come today. So if we kind of go today, basically, so we basically are here where we see all these different kind of robots, and they are increasingly kind of being adopted in industry as well, in the ways that, for example, for some small and medium enterprises who may not be able to afford a large expensive robots, the smaller industrial scale robots have also come, like for example the URs, which you see here, one of the URs, and they can work in close collaboration, so they're very safe to work with humans, and you can actually do that. The other robots, as you see, that there are walking robots and underwater robots, and another thing which has kind of gone also significantly mainstream is surgical robotics, in the sense that a lot of hospitals have this intuitive surgical, for example, and other companies which maybe they have these devices. So so it has gone definitely mainstream, and also it has, for with the advent of the drones and the Roombas, so we also now have seen them in our homes. So looks like they are increasingly kind of getting into our our spaces, different spaces, and it's only going to accelerate. And so on the bottom left also, you see kind of a robot that kind of is a little bit different from all the robots, in the sense that it is continuously deformable. It can do large deformations. So it's slightly different from all these other robots in that way. And that's what I will kind of focus on also towards the end of my talk today. So yeah, so just to kind of give you a brief overview of kind of the projects that we are doing right now. So one area that I've been interested in for some time is, is bilateral telemanipulation, which is on the top left you see there. So here essentially what you can do is you can, let's say you have a mining project, for example, and it may be so that some of the devices people don't want to work in that environment. Maybe it's hazardous, or maybe they don't know that environment that well. So what bilateral teleoperation allows you to do is, for example, operate a robot remotely while kind of manipulating something in the environment. For example, an excavator. I'm just giving you a broad example, but if you want to do fine manipulation, you will need kind of a link manipulator to do that. But it's possible to do these kind of tasks. And the idea is that you should be able to feel some idea of the force that is coming back, because we indeed use the force as a very key mechanism for a lot of manipulation. So in this, basically, you are transmitting some signals back and forth, and I will talk more about it, in a subsequent slide. Another project that is going on is with the Army. Basically, it's on maintaining connectivity in network robots, so they can actually do something outdoors that is useful. I'll also talk about a little more about that. The two projects that I would like to talk about, which I am not going to talk about later, is one that is recently started, which is actually covers broadly underwater robotics, but specifically it is on the life cycle of growing oysters on different parts of USA on the different bays. So basically, we want to be able to right now the way it's grown, people plant oysters, seeds, and then basically they have no idea where they're planting them, and over time they kind of they don't map it. They go periodically, they go and check some things, but they have no idea what conditions are good for growing oysters, how to kind of actually take them out after the thing that they have grown through their life cycle. So this project essentially is on basically using underwater drones to be able to map underwater environments and basically track the production of oysters as they go through their life cycle. And this has, apart from people in academia, this has other folks involved as well. And so for example, in US we have something called extension, which are kind of people who are very close to who are actually maybe doing active research and have some related oyster farms as well. Last thing that again I will not talk about is that we are kind of doing some projects which map indoor environments and allow navigation in those environments. So what you see here on the right is actually a map that is that a robot kind of came up with. So basically, the green thing that you see there are the glasses, basically glass walls. So we were able to create this map, and then we overlaid this map on the actual floor plan of the building. So you see that this kind of is a very robust and way of mapping indoor environments. And currently, we are working on robust navigation in so that when a lot of people may be moving around in those environments. So I'll first talk about a little bit about bilateral teleoperation and then a little bit of connectivity, and then I will kind of go to the soft robot control aspect. So as I mentioned earlier, that in bilateral teleoperation, essentially what you are trying to do is you have a robot that is maybe close to a human operator, and then you're trying to control a remote manipulator. Remote manipulator may be in the same room. Maybe let's say I'm sitting here, one robot is with me, and another robot is in the conference room in IIT Kharagpur, right? And we want to be able to kind of control the robot to kind of do exactly as the person is commanding it, the leader is commanding it to do, and at the same time I want to feel the force back. So just to get an idea, we have some robots, and we kind of developed a small demo to be used in actually an education conference. So just to kind of give you an idea what it can do, for example, these are small robots that are actually portable. And what you can do here is, like, let's say you want to draw something, and you are drawing something here, and the other robot is actually exactly replicating it, and you will get a feel of the force coming back from that environment as well. So this is just a kind of a small example, but you can do it to more complicated tasks, which involve some maybe drilling or other related tasks that may need to be done. Of course, surgical robots do that, but they don't have force feedback on them right now. And also, some robots that our army uses, for example, in remote, detonation or explosive ordnance. Either they want to defuse the bombs or something related. Yeah. So what are the challenges that come in this problem is that, because you kind of, let's say if I'm sitting here and I'm sending a signal to IIT Kharagpur and getting some signal back from there right now. So there'll be some time delays that will come about, and maybe some data will drop. And so how do we take care of these issues, for kind of highly complex manipulators is what, is some of the research challenges come about. So, and other basically what happens is that, let's say it's you have like you have a robot that is like a walking robot. So in that case, it's not as simple as a simple link robot. So in that case, you kind of, you have to, you are manipulating many degrees of freedom. So other issues come about. And so in some cases, you also need to, basically be cognizant of the fact that you're getting overloaded in doing some task. So in those kind of situations, a lot of times what we do is we use some kind of, basically what is called, subtask control, where we kind of ensure that the operator is only focused on doing a certain task, whereas the other things like joint limit avoidance and all these kind of other things can be taken care of automatically. Another, thing that is becoming increasingly, as you know, so as you see that 5G is coming about, there is a lot of interest in trying to, take some tasks such as learning or control, off the robot itself. So the robot maybe doesn't have too much computation capability, but it can be done off, maybe on the cloud or somewhere, and it can be deployed on the robot itself. Well, it's hard to find 5G chipsets right now because of some other reasons, but we were trying to do it for some other project, couldn't find it. But yeah, so that's kind of some of the things that you can be interested in. So again, so in this case, what happens is the network issues start coming up, and we want to kind of address them. And one of the issues is time delay. So just to give you an idea of what small time delays can do when you're trying to do either in teleoperation or network control. So you'll see that I'm just trying to regulate this robot to a fixed joint angles. And there is a very small, maybe, if I remember correctly, maybe around 30 millisecond time delay, 30, 40 millisecond time delay. And that delay basically will completely destabilize the system. And so when you're doing this, for example, when we are drilling, right? So we find that we are kind of, banging against the wall if we are not applying the appropriate force. So something like that can also come about, so you want this action when you're doing industrial tasks, you want this to be very stable. And, so that's one of the things that we kind of we have worked on. And for example, now the same problem, if we kind of use some of the algorithms that we have developed, which kind of make sure that things behave in a normal way. So you can see that, things are, you can make the system really stable. So this was just one, the problem that we have worked on for some time, and now we are actually using it for soft robotics as well. So I'll show you that later. Another problem that project that is going on is on connectivity control. So for example, when you are deploying multiple robots in some scenarios like disasters, or you're trying to do first responder, as are using those robots. So what happens in, for example, in urban environments is that the Wi-Fi and VHF bands, they, because that's one of the, typically what will happen is that you will use those kind of communication medium to communicate between different robots who may be kind of doing a task jointly. And what will happen is that if you use this Wi-Fi, or other high frequency bands, ultra high frequency bands, what will happen is that the multipath will kind of, your signal will drop a lot. It's same as, in a house, there are dead spots here. But now you are kind of not just receiving signal, you are kind of doing some maybe control over these signals. So you need to really kind of take care of things. Also, they will not go inside buildings. Let's say I want to talk with my robot, which is kind of gone inside and trying to get somebody out of a building. So I need to be able to kind of communicate with that robot in some way. It's very hard to do it with these kind of, wireless devices. So what we kind of, in collaboration with the Army Research Lab, So the Army Research Lab basically was coming up with compact, VHF, low VHF antenna. So VHF is, let's say, around 30 megahertz to 300 megahertz. So around that, those bandwidth. So this frequency range. So basically, they had come up with a low frequency antenna. And so what happens is when you use robots with these kind of antennas, you can actually increase the range. So the figure on the right kind of is just kind of illustrating what the range increase come by this kind of using this low VHF antennas. So our project on this was basically how can you use, you have the, early, I'm sure it's still there, but in early days when I was growing up, all we had was those antennas that were there on the top of our roof, which was catching Doordarshan and other related channels at that time, primarily Doordarshan. So this is something like that you are kind of using robots. Imagine these two robots are like those two, one of them, the metal bars that were there, some were smaller, some were longer. So they are like, these robots are like those metal bars. Some are actually emitting, some are reflecting, and some are directing the signal. So how can we increase the connectivity of robot communicating with each other by using these, what we call antenna arrays? But the antenna, so for example, in this case, only one robot may be transmitting. The others are helping. The other robots are making a team. They're forming a formation around the robots and helping it communicate and maintain communication throughout a task. So you will never. So what algorithms we have come up with, they guarantee that if you start with the fact that you're connected when you start, you will kind of remain connected. So right now we're trying to show some experiments where you can actually do some control with one robot and the other. One is inside a building, other is outside a building, and how can you actually do that? So these hopefully in next year or so we should have those experiments in place. Yeah. So going forward, so let's go to soft robots, kind of the topic of a main topic of the talk today. So what has kind of garnered the interest in soft robots, right? So for example, in a manufacturing environment, a lot of times what may happen is that you may want to, so primarily the interest has been in grippers right now, till now. Actually, there is a commercial firm that has been quite successful in actually not only doing research, but actually going ahead and selling it commercially. And they're, I forget the name of the firm. I think it's called Soft Gripper, something of that nature. So what has kind of got, some of the inspiration has come from basically octopus in some ways and other things that we see in nature. But basically, the constraint with rigid links or is rigid robots is that I have limited degrees. There's some places in my workspace I can't really go. There's limitation with that. And the other thing that happens is that if I'm trying to grasp something, if I try to grasp soft objects, right, like say a food item, right. So in that case, the grippers that are there currently, they are not very feasible. So in those kind of environments, soft robots come in very helpful. And because they are soft, they can actually go around places where it's just impossible for rigid robots to do that. So there's a lot of kind of, and they can go through environments. Let's say there's a video out there. Basically, you can see an octopus going through a very narrow tube, so it can transverse. It can locomote at in very restricted places, grab different objects of different dimensions, and place them from one place to the other. So these kind of things are kind of what are inspiring the interest in soft robotics. And so, this is just a brief categorization of what do we kind of mean by, from basically soft robot. What is a soft robot, right? You can ask that question. So basically, in this sense, let's say you have a rigid robot, right? So you may have redundant robot, which have redundant degrees of freedom, maybe hyper redundant, lot of redundant degrees of freedom, and then we come to continuum robots and the soft material, which basically we can see large deflections. Okay, so we are not talking about small deflections here. We can see large deflections and we want to control those large deflections. So, for example, when you have beams, we derive these models, but we, are typically trying to do with small deflections. So here, basically, we are trying to be able to control large deflections in these robots. And the challenge that comes about is that it's a very integrative task. Like I can't design. So in traditional rigid robots, somebody may be designing it. right? Some manufacturer has designed it, somebody else is developing a control algorithm, somebody else has a sensor for it, right? As long as it fits the specifications. The challenge here is that it's a very integrative task in the sense that everything really influences, one thing will really influence what I can really do with the other. It also influences in the rigid case, but it's the influence is much more significant here in soft robots. So this is one of the soft robots that we have been working with, that's on the left top there. It's actually what you see there is a 3-link robot, which is kind of composed of 3 different links that we have there. And as I said, that it has a lot of compliance, right? Dexterity and obvious safety that is kind of important in some manufacturing environments, because these days we would like humans to work in those environments, and that's one of the things that comes about, that if you can guarantee safety, it becomes a easier. Programmability, safety, there are some of the issues that are important in manufacturing environments. Yeah. So I will, spend a little bit of time on what kind of modeling things that we are going through right now. So here, basically, what modeling, this is the challenge, because if I were to write down, the model for it, basically infinite degrees of freedom, you basically have modes that keep on coming, and so people have come up with simplifications, and so I would like to kind of stress one fact that a lot of folks, what I'm talking about right now is trying to do closed loop control of these robots. A lot of robots that are existing right now, they are primarily open loop, because it's just for the very fact that it's very hard to control these, model them and control them is now highly non-trivial. And sensing is also a challenge, which I'll kind of discuss shortly as well. So one of the models that we have been working with right now, and we are refining them as well, is what is called the piecewise constant curvature model. So basically what you assume is that, let's say you have a 3-link robot, then each link, basically essentially we are controlling the first mode, if you will, right? So if you think about it, we are controlling the first mode, okay? And every link has a first mode that we are trying to control, and we are kind of putting these links together one after the other. So it's a constant curvature model, which is called piecewise constant curvature model, because that's what it is. Yeah. So people there's some literature there. I'm not going to detail the literature right now. So people have tried more complex model as well, but while they are, it's a more precise way of modeling them. It's hard to control using that kind of a model. Basically come up with model-based controllers for them. People have also tried model-free controllers using machine learning methods. So I will argue, I'll have one kind of comment later on, which basically kind of says that, using my limited kind of experience with machine learning in robot control, estimation, and so forth, what I figured out is that it's better to kind of do it piecewise. Use physics where you can, and then use machine learning where you literally have no idea what to do. Okay, in the sense that machine learning is, the 3 kind of main things that you need for machine learning. One is, that there is a pattern. There has to be a pattern to kind of, between whatever you're trying to learn. Second, basically, you need kind of data. If you have no data, or not just no data, you need large amount of data. So if you try to do everything using machine learning, then the data problem will start coming in, especially if you use reinforcement learning, because it's very hard to gather the data from experiments, and you really need simulators, and other problems start coming in that case as well. You want to transfer that simulation. So usually what I found is a combination of physics-based methods and machine learning where you want to use them will come in helpful. But completely model-free methods are, not very generalizable, in a sense that if you do it for one, you want to not just do it for the one robot you have, but other people should be able to replicate it with whatever robot they have. That becomes the challenge in this kind of using completely model free for everything. And so once you kind of do this approximation, so what happens typically here is that, let's say, I don't know if there is any roboticists there in the audience, but what typically this is becomes a RPPR kind of mechanism, that what you're approximating it by, you have a mass in the middle, and if you do it for all the links, you can kind of come up with the Euler-Lagrange model that looks like this. So basically, there are some parameters that you do not know here. For example, the torsional damping and even the torsional stiffness is something that you don't really know. Maybe you have some idea of the other you can do, but these damping and torsional things you have to kind of estimate, and that kind of inspired some of the adaptive control algorithms that we kind of used for these robots later on, that I'll kind of briefly discuss. So it's a simplified model of the real object, but it works, as I will show you, it works reasonably well in experiment. But so there are some parameters that they're uncertain, and you either need to do system identification some way or the other, or do that and then go ahead and use some adaptive control methods when if you are trying to track. So the idea was that we wanted to.
Hello.
Yeah.
Sir,
yeah, please.
Can you elaborate how does it become RPPR, that is revolute prismatic revolute, right?
Yeah.
How does it become? Can you elaborate a bit?
So basically what's happening here is that you have, so this is an approximation, first of all. So LS, the length remains constant. The LSI that you see there, it remains constant, right? So the approximation is that you can take, so this is an approximation. It's of course like, approximation in the sense that you basically have, you see this, this QSI, and basically, so QSI basically is kind of the state variable, the curvature that we are trying to control, the constant curvature. Okay. And what this basically is that you're kind of saying that this can, of course, rotate. That's why you have this, the revolute there, right? But at the same time, it can extend as well. But the constraint is that LSI should be constant. So that's a constraint that cannot extend, which can happen in some robots, even soft robots, that it can, along the length also it can extend, but that's the constraint we put here. And that allows that model to go through, this model there. Okay. And I can point you to a reference, which kind of discuss in detail. Just send me an email. I'll just send you the reference back.
Okay. What is your mail? Later we can discuss it.
Yeah, we can discuss it. Okay, so basically the task was that we wanted to control this robot in the task space. Task space basically means that I want to control the end point of this robot and how its trajectory is moving, and so that I can control it in the XY plane right now. In this case, we were doing the XY. Okay, so you want to control in that plane. And these are kind of some of the standard methods that is there, that we have done earlier, and which are inspired by previous methods in the literature as well. I'm not going to the mad details here, but this is kind of, basically we did some adaptive control design because we didn't know this, as I mentioned, we don't know the torsional stiffness, the torsional damping, and we had some nominal ideas of what the nominal values were, but, we want to actually, we don't know and these values, and we don't want the, we want the tracking to be good. So basically we had to kind of, utilize some estimation algorithms, basically, which estimate this, parameters in runtime and then apply the control appropriately. So first I'll do a simulation and then I will show you an experiment of what we did. So in the simulation, so you basically have 3 actuated segments. Okay, and so segment 1, segment 2, segment 3. And you basically have some initial estimates of these parameters that I mentioned, which are all kind of stacked together in the theta hat vector that you see. And so this is just a simulation first that, so we are trying to kind of follow a desired trajectory, in basically in task space. And so you see that, that this is maybe challenging, depending on if you have a rigid robot, this kind of, if you have a complex trajectory, it may be not be viable to implement it. And some other things also I'll show you later, which are related to this as well. But this is trying to follow a trajectory, okay? And you see the parameters evolving, estimate is the estimate value. So they may not actually, they usually do not converge unless some other conditions are met. They do not converge to the great thing is that you actually do not know the real value of the parameters, but still using this kind of method, you can, do reasonable tracking. And this is again the parameter estimation. So this was the experiment thing, right? So this was basically experiment. So this is the setup that is there, and we want to kind of instead of so our this bar that you see here, it has kind of something which can be recognized by. So there is a camera which is tracking this. That setup will come. I'll show you that later. But there's a camera which is kind of tracking this and providing the signals to the to the controller to be able. So this is a pneumatically actuated robot, and it's kind of basically we are trying to track the reference, which is given by the blue dot, that covered thing that you see, that circle around the blue dot. Yeah, let's see how it works. So the noise is there. So one thing we would like it to make it, pneumatic actuation is there, so it's kind of. And this was actually really cheap motors, and sorry, not motors, like really cheap. What is a very expensive system? So actually build up. So that's one of the other advantages for soft robots. They are relatively cheaper to build, right? No mechanisms, that many mechanisms, no drives, So they make kind of not only they are safe, they can be cheap, but obviously one of the things that they lack right now is the appropriate level of rigidity, right? So because we need that rigidity in for some other tasks. So there's research going on right now that how we can kind of bring them closer and closer to actually how the rigid robots are there right now. So that's an aspirational goal, not there right now, a little bit far away from there. Okay, so again, so this basically, so that what you saw was just a tracking task. So you can use similarly a soft robot. Let's say I want, somebody is doing a task and they want to be able to control this again in some task space, and again feel some force back. So we can do a similar thing here as well. Yeah. So again, we have some trajectory tracking algorithms. I'll just quickly go through them. This is the setup that I wanted to show that we have, right? So basically, one of the key things that you see here is that I'm using the cameras and there are some motion capture cameras, and I'm kind of OptiTrack cameras, and I'm actually putting, tracking some particular, circular things that you see on top of these robots, which are helping me in estimating what the bending is, what that curvature is, because I want to control the curvature. So I need some way to sense that curvature. Question? Sorry, couldn't hear you. Is there a question?
Yeah, please proceed.
Shall I continue? Yeah, okay, I'll proceed. Yeah, okay. So basically what is happening is we are trying to control this curvature. So we need some way of sensing the curvature. So that is right now in this time being done by the camera. So that's a limitation, because how will I use this robot outside if I have to use a camera all the time, right? So that's a constraint that we recently have solved in one of the paper that is coming out in ICRA this year actually. Yeah. So that kind of motivated our next part of our research as well. I'll talk about it. Let me just show you. So we basically use, we have to, we need a torque signal, and then we have, we're getting PWM signals. So we first have to do some curve fitting to kind of match them up as well. And this is how the experiments look when you're trying to, so you see that there is one experiment which says without subtask control, and other says with subtask control. So that was one of the things I was mentioning to you earlier. The constraint put here was that some cases you can't go beyond certain curvature limits. Let's say I put a constraint that this robot cannot exceed certain curvature limits, right? Due to whatever reason may be there, right? So in first case, you see that the robot is allowed to bend whichever way it wants to in achieving its goal of trying to task something in the, in the XY plane. But in the second case, we can still do it with subtask control. We have to kind of not manually enforce it. We can add it in the controller. And similarly, we can, we can do some other tasks where we see where the circle regions are where it contacts an environment, and we can kind of feel that force back, from that environment. Okay. So what insights we got was that, there is obviously some practical issues that come about, which is, actuator saturation and all these kind of related issues where basically, because I have a limited torque, so I can't generate whatever torque my controller tells me to. I have some limits there. So how do we take that into account? This is a slow process, right? So some other things to accelerate it. And one of the critical things we came about was that I need to use this in unstructured environments, right? So how will I sense it, right? I can't have the camera everywhere I go in anywhere I want to do this task. So this kind of inspired in collaboration with colleagues who work on, sensing. we kind of utilized some of the sensing skin that they had come up with. So this sensing skin can be put on any robot, and what that does is basically it allows you to measure the bending strain. Okay, so from the strain, basically now how do you translate the strain to a bending angle? So that's where we use machine learning. Okay, so that's where we found the machine learning to come in very helpful. I'll just shortly show that. So that's again was like an intelligent sensor. You have a raw sensor data coming from this skin sensor, and how do we translate to an actual bending angle that we can use in our controller? So this is basically the sensing skin that you see. So this is a soft sensing skin. So it's on the sides, basically you see that it is on both sides measuring, because the robot can bend in one direction or the other. So bidirectional bending is possible. So how do we basically had to have this active sensing area on both the sides? Okay. So you can basically took our robot and we just attach this sensing skin on top of it. So this is the setup that you see there, right? So we have soft sensing skin A, soft sensing skin B, and this is kind of the thing we ran. And we were using the cameras basically now for actually getting the ground truth for basically ground truth for this sensor, so that we can train the machine learning algorithm. So the camera is using we are using vision to get the bending angle, and then we are seeing what sensor data we are getting from this strain sensors, and then we are coming up with a mapping between the two. Okay, and so this is where we kind of use LSTMs, which are one kind of deep this was a deep recurrent RNN that we used. And so in a machine learning pipeline, you have these different things like you have to do validation so that you select the appropriate parameters in a learning module, right? For example, early stopping and number of hidden units. So we did all that. So so basically you're doing a regularization, you are doing validation to select those validation parameters, and then we have a test set. So this was the performance on the test set. So as you see, the error that the C which was on the test set was relatively low. And again, this is for the bidirectional bending. Again, it was kind of we were able to have a reasonable error in our predicted model. So we thought the model was reasonably well, and then we kind of used this model. So now this is a machine learning model which is now being used as an intelligent sensor in a control algorithm. Okay, so when we use that, because I'm running out of time, I have 3 more minutes, so I'll just accelerate a little bit. So this is kind of the tracking results we got using this sensor, intelligent sensor, which has one component from machine learning for a low frequency tracking, high frequency tracking. So unidirectional bending means that I'm only bending in one direction. Okay, so you see here that it's kind of degree, it's not doing bidirectional bending, so it's above 0. The curvature is kind of you see it above 0, and here you see in bidirectional bending that you can go both ways. So in both cases it was performing reasonably well, and so we are happy with that. We are still trying to now get more high frequency target as well, but we are also limited by the speed of response of the of our system. So that's kind of a fundamental constraint that we have. So recently, what now we are doing is we are going from we are trying to do some more complicated tasks. So for example, one of the because we want to be able to, our idea is that can we make this robot do things that the rigid robot is doing right now, right? And as you see from the speed of response, and it's, first of all, it's slow. Another thing is that we are not what will happen is that when it contacts a surface, that constant curvature assumption will be violated, because it will start bending in ways that are not satisfying that assumption. And so we want to be able to do really more sophisticated control of the soft robot. So one of the things that we are starting with right now, and we have some results. I don't have experiments to show that right now. Hopefully this later this summer we will. But what we are trying to do is we have in control, one of the challenge benchmark tasks, they call it, is stabilizing an inverted pendulum. So I want to swing an inverted pendulum up and take it to the top and stabilize it there. So we have come up with some control algorithms recently that we are shortly about to submit to some conferences, and that basically we can actually do that. Okay, so you can take a soft robot and do much more complicated control and do some more challenge tasks that are very difficult to do normally. Even with a rigid robot, they are not non-trivial to do. So how can we do them with with soft robots? So we don't have experiments right now for that, but hopefully next time. So I just like to kind of end the talk with kind of some take-home messages that I thought were maybe relevant. So you know, the transition pace of robots to the consumer world is really accelerating. So you know, hopefully next 10-12 years we will have much in-depth integration coming about. In industrial robots, one of the key things that is there that they need to work safely with humans and other robots. So how do we ensure that is very important. And for industrial robots, typically we need one of the key things is, for example, welding. We need tracking algorithms that work well, despite maybe flexibility of the robot joints and stuff like that. And the network is also increasingly becoming a very critical part of sensing, monitoring, and controlling these systems. But they bring about some safety and security issues which also need to be dealt with. And in soft robots, the designers of the sensors, the designers of the robot themselves, and the people who are designing the control algorithms, they have to work together. It's a very integrated task, and it's hard to kind of separate this out particularly for soft robots. And I already mentioned the last point that we have used learning and for example, in sensing, developing intelligent sensors right now. We have also used a little bit in control as well. But what I feel is that completely model free, that I just take something completely model free in this case would be, I take the raw sensor data that I got from my sensor and come up with the control algorithms for it. So that will be one example of a completely model free approach. It's not, first of all, it may be not useful. And I think that we can really use the physics as much as we can, and then use machine learning where really we kind of run out of, there's a pattern, but we can't, detect it ourselves. So we need the machine learning to detect that pattern for us. So that's where it becomes very useful. So yeah, so kind of that's the end of my talk, and I'll kind of be happy to take any questions that may be there.
Yeah, thank you. Thank you. It's a very nice, the presentation. And you have rightly told that, the industrial robots need to work more safely with the humans and other robots, because we are residing today in the Industry 4.0 era, and we are working with the hard automation in the robots. We are getting transited towards this, the flexible automation and all. But
right.
The concept of the soft robots will be very much needed and useful for the tackling the dynamic unstructured the situations, which is very very much needed. At the same time, I can understand that the communication between the two robots, and that too operating in the dynamic situations, that would also very much the difficult. So so it's a wonderful talk, and